take a unit sphere and a unit square. And by unit, I mean, let's assume that the sphere fits inside of the square perfectly. I drew it a little too big. Perfect, just like that. The only thing you have left over is space around the corners, right? As the number of dimensions increases, and you can kind of see this just with a simple test, right? Here's a square, here's a circle. Okay, there's only this much area, right? Now we have this much volume, and it's that much volume times 8 rather than 4, right? Because there's 8 corners. If you go into higher and higher dimensional space, and you can confirm this just by doing a little bit of geometry, the excess area at some point actually overtakes the overlapping area, and eventually you get to the point where the vast majority of it ends up being in the corners. And that's really significant because it turns out you get extremely biased in high dimensional space with hypersquares, whereas with spheres you remain unbiased to infinity. In the case of a neural network, we're initializing a weights vector that has how many weights in it? Well, you started with 784 feeding into 80, so 784 times 80, plus 80 times 30, plus 30 times 10, and then there was also the biases, so we need to add 80 plus 30 plus 10. Whatever that adds up to is the total number of weights. You see that that's kind of a big number, and if you start adding uniform values to it, you're injecting a lot of bias to it. Okay, having said that, after I made all that big point about it, I really just wanted you to understand it. It turns out it doesn't really matter. Plenty of people do neural networks with uniform distribution values, and it works just fine. Okay, they do have to be random though, and not constant, and that's what I want to talk about next. But that's why we like the normal distribution, is it's unbiased and it makes us feel good to not be biased. Although because we have nonlinearities, it turns out that that introduces an unknown effect, and so we don't really even know if being unbiased is important. In fact, being biased might even be better. And so I really don't know. Okay. Having said that, where am I? This is a pencil. I can draw straighter lines than that by using the straight line tool. If you set a pencil on its tip, I should have just used a real pencil. What are the odds it's going to continue to stand? Almost zero, right? It's very hard. Although, have you heard the thing about Christopher Columbus asked if he could balance an egg on his head? They said it was impossible, and he's just smashed it, and then it stood there. And he said, ah, ha, ha, ha. I don't even know if that's a true story. Anyway, my point was, in the physical world, it just would not happen because chaos. There are imprecisions in the table you set it on. It's very unlikely the lead would be perfectly uniform. There's no way you'd be perfectly vertical when you let go of it. There might be wind in the air. For whatever reason, it's going to get off by a little bit, and the more it gets off, the more it's going to throw itself off. In a computer simulation, though, if you had a pencil, it's very easy to perfectly set a virtual pencil perfectly straight up and down, right? And if it is, simulated gravity will have exactly the same pull on both sides, and no matter how many iterations of simulated physics you run, assuming it's truly fair, the thing will just never fall over, right? A similar thing happens with neural networks, and this is the analogy. They keep using the pencil analogy, so if you ever see that in literature, it will now recall to you this lecture. Imagine we have 3 inputs, and we'll say 4 outputs, just so we can have some non-equal number. And these are all fully connected. Now imagine that every single one of these weights is initialized with the same value, whatever it may be. Well, let's start with 0. Let's initialize all the weights to 0. What's going to happen when we do our first forward propagation? Everything's going to be 0, right? Now we could imagine there are 50 layers if we want to do it again. But once everything here is 0, now it doesn't even matter what the weights are because the activations are all 0. So what reaches the end is going to be 0. What's the error going to be? It's going to be exactly whatever the target labels are, right? Well, you put that on here as the blame, and then you backpropagate it across 0 weights. No blame is going to survive across 0, so no blame will be received by this layer. When it comes time to update the weights, it's the input value times the blame. Remember, that's going to be the target labels. But the input was, those are the input values. That actually will update the weights. It doesn't fall apart until you add a second layer. I probably knew that, I just wasn't thinking about it. Now we have a second layer. Okay, if you initialize the weights all to 0, nothing reaches the end. The blame stops right here, doesn't get backpropagated. These weights never get updated, which means they stay at 0, which means the next pattern presentation does the same thing, which means you never make any progress. So do you agree with me that 0 is a bad starting point? We can't do that. Okay. Now,
so the first time it updates the weights in the second to last layer?
Let's see. You're right, that would eventually start working. Okay, I'm going to have to think through this systematically. Let's do it, and help me not make mistakes because my brain is, the flu's still in there. I'm still trying to get it out. Okay, a bunch of zeros multiplied by, a bunch of correct values multiplied by zeros are going to all be zeros. A bunch of zeros multiplied by anything comes out 0, 0, 0. We predict a 0. Now we compute the target minus predicted. We get the blame. It's going to be the target values. That blame, we then try to backpropagate by multiplying by the weights, which are 0. So no blame, no blame, no blame. So the only thing that has blame is this very last set of units, right? Okay. Then we try to update the weights, right? Nothing updates except potentially this last layer, and we try to update it by taking the values that were fed in times the blame, but the values that came in were all zeros. So those zeros mean these weights never get updated either, which means we're stuck, nothing will ever change. So zeros mean dead neural network. You can't have a neural network initialized with zeros. Okay. Now let us suppose we initialize everything with the number 0.1. I picked that because it's small, but not impossible to reason about. Oh, heck, let's just do 1. That's even easier to reason about. Okay. Every weight in the neural network has the number 1 as its value. We feed in some meaningful numbers here, and they're all different, right? But do you see that because these layers are fully connected, every unit feeds into every other unit? Do you see that all 4 of these units are receiving the exact same signal? Now, it's going to be some meaningful number, right? It's basically the sum of all of the inputs, isn't it? Okay, so whatever the sum of the inputs is, that's being fed into these guys. And that's going to go through a nonlinearity. Who knows what value it is, but they're all the same. And then that who knows what value it is going to be summed together into these units, and then run through some nonlinearity, and then sum together and run through here. The point is the same numbers are going into all of these units. Well, if that happens, then the blame will be target minus whatever that number is that they all share in common. which might potentially be different per unit, right? Okay, but then when we backpropagate these different numbers, do you see that they again are multiplied all by the same ones, and so they come out, the same blame is placed on all of these units. And then the same blame goes to all of these units, and the same blame goes to all of those units. Do you see that all units are receiving the same amount of blame, even though they receive different inputs and had different output layer blames? Okay, so then it's finally time to update the weights. Let's see. This layer had uniform blame, but different inputs. But the values between the inputs and each unit are this. So the same blame and the same input. Do you see that all of the weights coming from this unit will be adjusted the same? Because the input's the same and all of these blames are the same. Okay? And all of the weights coming out of this unit, they're not tied to all the weights coming out of this one, but they are all tied together because they all share in common this input value and these blames are all the same. So although these weights may be able to separate from each other, they can't separate from each other. That didn't work out. The intra won't work, but the inter will work. Here's what I'm saying. They can't ever get apart. No matter how often you present patterns to it, and no matter how much diversity there are in the patterns, if you pull these ones over by 0.28 amount, it pulls all of them over by 0.28 amount. And so they're kind of being trained in total syncopation like this. And what never happens is they get apart from each other and do something meaningful. So basically, the grand no-no is don't initialize your neural network with anything constant. You need just a little bit of uncertainty or diversity to it to make it work out. So the idea is start your pencil leaning just a little bit to one side, and then your neural network is capable of learning. You just can't initialize with zeros or a constant value. Okay. Having said that, even if you initialize with a lot of constant values, it usually works as long as you don't get every last one in the entire layer. If you get them all, you're pretty much dead. And you don't want zeros either. That's bad juju for neural networks. Okay. Next bit of intuition. We don't usually want to initialize with big values. Here's why. So let's get to come on, give me a plotting tool. Okay, here's a picture of tan h of x. Let's assume for right now we're just doing a single linear layer followed by a single nonlinearity layer. So basically it's trying to fit this tan h shape to your data, because that's easy to think about, right? If that's the case, if I use very small weights, like 0.1 times, if I have very small weights, they'll go through the linear layer and be multiplied by very small initial weights, and then they'll go through the tan h. So the equation will look kind of like this. This is tan h of 0.1x. As I make those weights bigger, this is 0.2x, this is 0.3x, this is 0.4x, this is 0.6x, this is 0.9x, this is 2x, this is 7x. You see what's going on, right? Is this bend is getting pretty darn sharp. So what happens is when you initialize with tiny weights, you're essentially starting out doing linear regression. In fact, you are doing linear regression because in the Let's go back to 1 there. In the vicinity near 0, that thing basically is the identity function. So the nonlinearity does nothing, right? As long as your values are really small. So at first, a neural network really does do linear regression. Imagine now you have some data. Isn't the first thing you want to happen, imagine your model is just a straight hyperplane. You kind of just want to rotate that plane to fit the data as quickly as you possibly can, because that's what linear regression is. But then, after it fits it with the plane as well as it can, then it starts bending itself to reach out and fit the bends where is needed. And I claim that's a rather intelligent way to fit data. Okay? By contrast, suppose we started with large weights. That's kind of like, imagine your data is a bunch of points floating in Euclidean space. And imagine the neural network as a great big sheet of aluminum. If you wanted this sheet of aluminum to fit to all of those points in space, would you rather start with a nice smooth piece of aluminum, or would you rather start with one that was all crinkly and bent up? The answer is smooth. Okay? Why do you want it to be smooth? Because the first thing you'd do is you'd iron it out, and then you'd start bending it to fit those points, right? Because you don't want arbitrary crinkles. Remember the whole lecture about under-constrained models and about how bad it is to, it violates Occam's razor if you're adding things to your model that have no justification in the evidence, in the points. Well, that's what you're doing if you have a bent up neural network. So we start with tiny weights because that makes a nice smooth model, and we fit as well as we can with a smooth model. And as the weights grow on their own, because we're learning to make them grow, then it starts bending when it needs to. Therefore, the general wisdom for initializing neural networks are start with tiny weights, but not 0, because 0 is too tiny. So don't go too tiny, but be pretty tiny. And that way, it will start learning in an intelligent manner and will fit to your data as well as it can. If you start with big weights, then you get big bends that learn arbitrarily biased things that you didn't intend to put in your model. Yes?
If you use big weights, doesn't your activation function just kind of become like the step function?
Yes, absolutely. So as we keep growing this thing, here's 9 times x. That's pretty darn close to step. And if I do 19 times x, even closer, there's 190 times x. There you go. Now it's the step function. It's still not, but it's darn close.